Hi, and welcome to the fourth and what I think are the most interesting lesson on exponential models, because now what we're trying to do is find a model for real data. Real data doesn't follow the niceness of everything being perfect and accurate. It's generally messy, and we generally need to find averages or lines of best fit. So if you look here, we've got the total number of confirmed cases of COVID-19 from the 23rd of February to the 20th of March, to the 21st of March, roughly a month. The month where this was really starting to kick off, and everyone was saying that this is exponential growth. So let's have a look at it, and you can see with this graph that it does look very much like exponential growth. Problem is, there's a lot of things that look like exponential growth. Even a quadratic curve can look a bit like an exponential curve. So what we have to do is we have to play around with things until we get what we think is a straight line. And when I say play around with it, I mean literally just taking the logarithms of different variables and plotting them against things and just playing around with it until you have a straight line. And the reason is because straight lines, we know a lot about them, and it's much easier to estimate properties of straight lines. We know, for example, that we can use the formulas y equals mx plus c, or if we prefer y minus y1 equals mx minus x1. And as long as we know just two pieces of information, the gradient and the y-intercept, or here the gradient and one other point on the line, then we can find its equation. And we're going to do exactly that. So here what I've done is I'm taking that month's worth of data and I've plotted the time against ln of the total number of cases. And you can see here that it is broadly a straight line. Okay. So let's use this, see if we can find a mathematical model for the first month or this month's worth of data. So let's, first of all, let's take this graph and change the axis at the bottom. I'm going to relabel this, the 25th of February, as 0, and every day has then one more than that. So this t is going to be the number of days since the 25th of February. Okay, which means we're going to want to have a y-axis of this, and like I said before, this is ln of t. And so we're going to plot a straight line on it, if this works. There we go. So there's my line of best fit. Notice it's not perfect, but it's pretty good. And we're going to take a couple of points. So first of all, let's take the point down here, 0, 3. Notice it's a bit of an estimate. If you're doing this for real, you'd want it to be slightly better. And I'm going to take this point over here. Okay. And from this, we're going to create a triangle because we want to be able to find the gradient of y equals mx plus c. And the gradient of the line. So measuring that, that's 20 days difference from 0 to 20. And here we've gone from 3 to 8, which is a difference of 5. So we get a gradient of 1/4 and a y-intercept of about 3. So now what we're going to do is we're going to plug this into our y equals mx plus c equation. Okay. Now y in this case is ln of the total number of cases. So instead of y, we're going to write ln t equals, and then m times x. So m is our gradient, 1/4, and x is, the x-axis is our t variable, time, little t, sorry again for the confusion, capital T, little t. And then plus c, in this case, the y-intercept is 3. Now, what we want to do now is convert this, change this, rearrange it so that capital T, the total number of cases, is the subject of the formula. This will give us a model for this scenario. If we take the, or raise e to the power of each side, we're going to get e to ln t, e to this, and that's going to cancel the e's and the lns because they're inverse functions. And this side over here, we can write as, using our rules of indices, as e to the power 3 times e to the quarter t. Now, e to the power 3 is just a number, it's about 20. And so this gives us a model. T is equal to 20 times e to the power of 1/4 t. And this fits with our generalized model of an exponential problem. Therefore, A is 20, K is 1/4. Let's remind ourselves of what A means. Now, A is our initial conditions. When t is 0, we get e to the power 0, which is 1. And so y would be equal to A when t is 0. So in this case, we know that 20 is our initial number of cases. For here, t is 0, there were about 20 cases, and there were 24 to be precise, and if I'd been a bit more accurate, we might have got a better result there. What does this e to the power of 1/4 mean? Now, this is going a little bit beyond what you guys need to know, but it's really worth trying to understand the meaning of things. Who cares if we've got an equation if we don't know what it means? So what does this mean? Well, this thing here, e to the 1/4, is being raised to the power of t. So if t was 1, we multiply by this once. If t was 2, we multiply by this twice. If t was 3, we multiply by this 3 times. So every day, we basically multiply by e to the 1/4. And so let's find out what e to the 1/4 is. E to the 1/4 is about 1.28. So it's about a 28% increase from 100%, that's your 100%, 100% plus 28% every day. And so we could ask ourselves, how long is it going to take us to double the number of cases? That's often something that people are interested in. So here we're going to say, right, what's e to the 1/4? How many of those do I need to make this equal to 2? That would double the number of cases. So e to the 1/4, to what power, how many days to get the answer 2? And if we solve this, we're going to get t equals, sorry, 1/4 t equals ln 2. And that is, so t then is 4 ln 2, 2.77 days. Basically, it's doubling every 3 days, which is exactly what was going on at the beginning of the coronavirus outbreak in the UK. And so here we have basically a mathematical model looking at real life data for the first month or so, creating a mathematical model. Now, bear in mind, most of this data is very quickly out of date because actually you can see it here, it's starting to curl off. And thanks to the hard work of many wonderful people, that's exactly what happens. So it doesn't continue to grow exponentially up this way, it starts to tail off, and that's due to the lockdown measures and all of the difficult things that people have had to be doing over this last few months. Let's have a look at a slightly different example. First of all, let's outline the steps that we've just gone through. First of all, we plot our data and we experiment with logarithms until we're able to find a straight line, because we can use straight lines and find gradients and y-intercepts of straight lines much more easily. So once we found the equation, that's what we do second. We find the equation of that straight line. And then starting with the equation of the straight line, we then want to rearrange to make the measured variable, the thing that we're interested in finding out, the subject of the equation. And that is what our model is. So here, let's have a look at this data. Here I have taken or made up some data on what's called black body radiation. It's where you take an object, like a sphere, a metal sphere that's black, and you heat it up to very hot temperatures. And as you get it hotter and hotter and hotter, it gives off light. It starts glowing red, and then as it gets hotter, it becomes white hot. And the amount of light that it gives off is proportional. Well, sorry, it's not proportional. It has some relationship to the temperature. And maybe as scientists, we want to find out what that is. What is the relationship? We don't know if it's exponential. We think it's some sort of power rule. And so what we do, we play around with logarithms. We find, hey, look, we've got a straight line here. that's going to work. So again, y equals mx plus c. In this case, gradient is 8 over 2, which is 4, and the y-intercept we can see is 3. So let's create a model from this. Our y-axis is ln of b. I'm calling b the brightness. You could use luminosity or whatever to be a lot more technical, but we'll go with brightness just to be a bit, keep it simple. And then the gradient of this line is 4. X is the logarithm or ln of the temperature, capital T, and the y-intercept is 3. Okay, so now what we want to do is change this, rearrange it until we've got an equation where B, the brightness, how bright will this object be if I raise it to a particular temperature? That's the question. So, ln of B, let's take the e to the power of ln B and let that equal to e to the power of the right-hand side, 4 ln T plus 3. Okay, sorry, do that properly, plus 3 up there. And now we can start to use our rules. E to the power of ln of B will just be B because inverse functions cancel. And here we can write this as e to the power of 3 sorry, I just lost my track. Okay, e to the power of 3, and then we're going to get multiplied by e to the power of 4 ln T. Now, we can change this around a little bit. We can use the power rule for logarithms. We know that 4 ln T is equal to ln of T to the power of 4, the same thing. So we can now say that B equals e to the 3 times e to the ln T to the power of 4. Now e to the ln is going to cancel, and we're going to be left with B equals e to the 3, which from before we already know, that's about 20. Let's forget that. 20 times. Now e to the ln is just cancel each other out, so we're going to be left with T to the power of 4. And that's essentially our answer. So we don't need to write that again. Okay. This is our model. We know that B, the brightness, is proportional to the temperature raised to the power of 4. And there we have our model. So make a note of those 3 steps. Get a straight line, use a line of best fit if necessary, find the equation of that straight line, and then starting with the equation of the straight line, rearrange until you make the variable that you're interested in the subject of that equation. You now have all the information you need to have a go at exercise 8D, okay, and the mixed practice. Do post comments and ask questions on Google Classrooms if you would like any help. Take care. Have fun.